Assalamualaikum. My name is Muhammad Ahmed. Today our topic is 2D force convection that we are going to perform on ANSYS. Our problem is that a fluid enters in a pipe of radius 0.0294 meter of length 6.045 meter at constant velocity 30.06 meter per second and temperature 298.15 Kelvin. We have the following fluid properties that are of air. Boundary conditions that from 1.8 meter to 4.27 meter length of pipe, we are going to heat them. Wall roughness 0, wall thickness 0, wall heat flux from 1.83 to 4.27 meter length of pipe is 5 to 10.85 watt per meter square. Ambient pressure is 98,338 Pascal and outlet gauge pressure is minus 112.3 or 97225.9 Pascal. Basically, we are going to use ANSYS fluid and we have to calculate and plot the velocity, temperature contours and wall temperature chart. Assumptions that flow is axis symmetry. This means that in cylinder coordinates r, theta and c there is no variation in the circumference direction theta, so the geometry in the simulation is a rectangle as shown and the flow is steady. We have inlet, outlet, center line, wall and red section is the point where we are giving constant heat flux. Its radius is 0.0294 and it's a center line. Now we are going to open ANSYS. For this we have to go on search bar and type workbench and then run it. It usually takes 40 to 50 seconds according to the speed of your processor and RAM. This window will appear after opening workbench. Now we go into toolbox and select flow fluid and drag it into projection schematic. Then we rename it 2D forced convection. Then we go on geometry and its property and our analysis type is 2D. Then we right click on geometry. It will appear new design modular geometry and then we have to select it. This type of window will appear. We go on tree outline and select XY plane where we are going to do sketching and then select sketching, select rectangle, go to region. When you reach on origin, P symbol will shown and then draw rectangle. Then go on modify and split into 3 sections, upper and lower wall. And then go on to constraint. Give equal length constraint to all 3 sections. Now go on dimension. and then rename their values. And set zoom to fit, go on dimension and use move there. Then generate it, go on concept, select surface from sketch, select the sketch and apply it, and then generate it. Our pipe contains fluid, so go on sketch, surface body, and from fluid or solid select its and fluid and go on generate and then save your project. Lecture, give it 2D forced convection. Then your project will save. Creating the geometry, right click on mesh and select update. When mesh is updated, you will have to right click on mesh and select edit. Then go on mesh, click on Z axis, zoom to fit, go on mesh, generate by default mesh, then go on mesh control, select face meshing, select the face and then apply it. Face meshing is used to create a structured mesh where the opposite edges correspond each other, and then you have to generate the mesh. After mesh generation, select edge right and left one, use edge filter and select right and left edge by pressing Ctrl. Two edges are selected and then give element type number of division and select it 30 divisions and then generate mesh. Then select upper and lower faces by pressing Ctrl key. Again go on mesh control, sizing, select element size and type element size value 0.03 meter and then generate the mesh. After the generation of mesh, you have to give name selection. Name selection is necessary because it helps us to specify boundary condition in setup. selection, we will go back to our slides and specify accordingly this diagram. Select edge filter, right, name selection, inlet, outlet, bottom center light by pressing Ctrl key. Selected wall, heated section. Last but not least, our domain, and then you can see their name on here. Go on file, save your project. After creating mesh, right click on setup and select edit. Select double precision. OK. This will open this type of window. Our problem is axisymmetric, that we have developed half pipe. Method is steady and pressure based. Then we go on models, turn on the energy equation. Then we go on viscous model and select K epsilon model, because we are going to solve for forced convection. Forced convection is basically related to turbulent flow, so we select K epsilon method. Then we go on materials. In fluid we select air. Our fluid is incompressible ideal gas, and select. And then close it. Then we will go into boundary conditions. Right click on center line and select the type axis. In heated section, type select it as wall and then edit it. In thermal, you have to define heat flux. In our case, value of heat flux is 5210.85. Select OK. Then go on inlet velocity, in which we have to specify velocity. In x direction, value of velocity is 30.06 meter per second, We also define velocity inlet temperature, that is 298.15 Kelvin, and then select OK. Then we go on insulated wall. In thermal, our wall is insulated, so our heat flux is 0 and heat generation is 0. Interior domain is type fluid, and we will define an outlet pressure. As you see in slides, that our outlet gauge pressure is minus 1112.3, that is equal to 97,225 Pascal absolute. Our turbulent intensity and turbulent viscosity ratio, we set it by default. We can change it, but we are setting it by default because we are not going in deep analysis of this stuff. Then we go on solution. In solution, first we go on solution method and select momentum, second order upwind, turbulent kinetic energy, second order upwind, turbulent dissipation, second order upwind, and energy is second order upwind. And then we go on monitors, residuals. Select OK. Then we go on solution initialization, select standard initialization, compute from inlet. On here you can see that our initial in axial velocity value, temperature, then go on random calculation, select iteration, number of iteration 500, and then select calculate. Our calculation is complete and our solution is converged in 404 iteration, and you can see on here that exponent -7, -7, -9, -10. Basically these are all the value of residuals. Yeah, this is kind of table like continuity residual, x velocity residual, y velocity residual, energy, k, and absent, and how much time it take to solve it and how much iteration it requires or left. Then we will go on file and save our project. Then we will go cut it, and then we will go in results or post processing and select edit. This one basically show us 3 messages. These are not errors. These are basically recommendation that given by ANSYS student to us. When we open the results tab, this type of window will appear. To view full domain, we select all these points, and on here we will select V. First we would like to see temperature contours. Select contours and type temp. Our location is periodic 1. Periodic 1 is basically the fluid, interior fluid, and our variable is temperature because we are going to develop temperature contours. And this one is a variable number of contours that you can put 100, 100, 200 according to your desire, how much you can see a variation in your results. I usually write to 101 and then apply it. As you can see, results have been shown, but our radius is too small as compared to the length of the pipe. So I will go on view. In view, I apply scale. In y-axis, I am scaling my radius up to 30 times and then apply. On here you can see only half of the pipe. As you know, on first part of our pipe is insulated, and then we supply constant heat flux, and then again our pipe is insulated. To see the other part of the pipe, we will go on default transform, uncheck instant info, apply reflection. On ZX plane, apply it. As you can see the whole pipe now. After creating the velocity vector, after creating the temperature vector, we will create velocity vector. For this, first we uncheck temperature contours, then go on vector, rename it velocity vector and select OK. In location, select periodic 1, variable of our is velocity, select apply, then zoom it and you can see velocity vector. Then go on symbol, because symbol size is too large, we have to reduce this. For this we will reduce symbol size up to 0.05. Now you can see the boundary layer. Now if we want to develop velocity vector, but in velocity vector we would like to see a temperature profile. For this we will go on color, in color select more type variable and select variable temperature and then apply. As you can see, temperature velocity contour, you can see how our temperature varies. As you know, our radius is too small as compared to the length of the pipe, so we go on view, apply scale of 30, apply it. Now you can see properly what is happening. Now we intend to draw wall temperature graph. For this, first we uncheck velocity vector, then we go on location and select line, wall, we rename it. We have to define 2 points of a line starting or ending. As you know, our pipe radius is 0.0294 and its length is 6.045 meter. So first we select this point of the wall, this point. Coordinates of this points are 0, 0.0294 and 0. Then we will define coordinates of this point, that is 6.045, 0.0294, and then apply it. As you can see, it's yellow colored line on here. We are going to define how much samples we require. We type it 50 divided into 50 samples. Then we will go on chart, rename it wall temperature chart, select OK. On x-axis our variable is x, on y-axis our variable is temperature. We can draw graph between temperature and length, pressure length, velocity, etc. I am going to select temperature and then apply it. It required permission from it. No, it required series, data series. I would like to specify data series is wall because I rename it wall, and then apply. I think I have select turbulence, edit dissipation. On y-axis I have to correct it. It's in temperature. Where's this length of the pipe graph?